Thank you, guys. Like Tony said, my name is Ben. I am doing a PhD at the University of Maryland in the Computer Science Department. But today we hope to present some tools that we work on at District Data Labs, which is a sort of an organization that Tony and Rebecca and a few of us in the room have been working on together for a couple years now, developing open source projects, mostly in Python, all data related, and we're hoping to showcase some of those projects today. In particular, Rebecca is going to be talking about Yellowbrick this afternoon in this room, so I highly recommend that you come and check that out. And we've been working very hard to get a release out so that you guys will have access to all the newest and latest and greatest stuff that we have in Yellowbrick. But for my talk today, I want the clicker to work.
What's the repo on your GitHub for this?
For the graphs, there are several. I'm not sure how that ended up at Twitter. All right. Now do you want to go? Yes. All right. So if you go to github.com/districtdatalabs, there are a bunch, and then all of the individual projects that I'm going to discuss today have their own repos. So Baleen and Minky, and I think Raleigh is the name of the notebooks for the graph analysis that we've done here. So there are a variety of stuff. So if you send me a message on Twitter, because Twitter just popped up, I'd be happy to point you to all the right places. But there's a few things going on in this talk. So the thing that I wanted to ask is, are graphs effective for analytics, right, for data science? I'm a computer scientist, and I think that computer scientists think about graphs all the time, right? It's a standard data structure. At the University of Maryland, in the sort of computer science 131 class, where we teach undergraduates how to program, their first tasks are to implement Dijkstra's algorithm and the Bellman-Ford algorithm and to create graph data structures in Java. And from that point on, their entire computer science career revolves, around graphs. And, I sort of have seen the community, and I've been a data scientist, and I've worked as a professional in the field. And I personally have tried to implement graphs for analytical purposes, but was sort of surprised that generally we as a community don't use them. We don't use these tools. They don't really make their way into like the statistical or analytical approaches. And so I sort of started to think, is this just a computer science thing, or are these things actually, usable or valid for data? And actually, should we use graphs at all? Right? Or, what is going on? What is the difference between what's happening in computer science and what we might think of in the analytical space? So in order to answer this question, I undertook an investigation where we tried to do an analysis, a text analysis, using graphs. And in particular, we wanted to ask the question, can we model time and dynamics, particularly change in time, over the course of, we were ingesting a bunch of documents, and can we look at how key phrases are changing over time? And does a graph model allow us to get more insight? Does it allow us to come up with better things than potentially our sort of standard machine learning techniques are doing? And we'll explore that throughout the course of the talk. So the first thing is, I mentioned this computer science background, so I want to tell you why computer scientists think that graphs are cool. The first is algorithm performance, and this is primarily the reason that we ask our undergraduates to implement graph algorithms and to understand them deeply, and that's because think about machine learning just as one example that you guys are familiar with. Machine learning is iterative. Right? So you do many passes on top of a single instance table, potentially optimizing some cost function or doing some other type of fitting. But that iteration can be seen as traversal. And the one place I tend to see graphs come up in our community is we express work as graphs, right? We have DAGs, directed acyclic graphs, that sort of express how information flows. But they're sort of high-level abstractions. We don't actually use them to do the thing. The other thing is that graphs are sort sort of already available in most domains. And when I sort of think about the world and I think about the way I'm going to model data, and when I start to think about entities and their relationships, I'm starting to do things in a graph way. So we have a native sort of performance benefit there. Graphs are natively parallelizable. So if you use gather, analyze, scatter model, you can put these things into a cluster and you can get big parallel benefits there. Graphs embed sparse data in a format that is very lightweight and compact. And the other thing I want to point out is if you see a graph implementation of a machine learning algorithm versus, say, the linear algebra version of that same thing, the graph implementation is much more understandable. And you'll have to take my word for that. But when that sort of understandability comes up, you can sort of make changes, you can look for places to improve, you can really work on the graph in the algorithmic context in a more meaningful way. On the other side, there's this sort of human aspect to graphs that I think maybe computer scientists have a little bit better of a handle on, that follows on directly from that easily understandable implementation. And that's that we as humans are built to immediately identify insights in interconnection structures. I don't have a good defense of why that is. I think I might, I might say that, now my computer's going crazy here too. Sorry. All right, we're back. I might say it's because we're social and we organize ourselves into relational structures. It might be because that's how we sort of view geography and we view maps and things. But the fact of the matter is that we sort of large-scale computations or analyses that take a computer a lot of time to do. A human can just sort of look at a graph and they can sort of easily figure something out. I think that Marco Rodriguez, who's one of the authors of the Tinkerpop library, he works for DataStax now, built a lot of parallel graph tools, sums it up best when he says that graph technologies ease the modeling of your domain, right? You can sort of easily come up with vertices and their relationships, or what are the entities and their relationships and what types of properties they have. And they improve the simplicity and speed of your queries. So this brings us to, I think, an important question, and it's what can we do with graphs? So in sort of standard computer science 101 fashion, I've grouped a lot of different algorithms into 4 primary classes, but I think they express how we might think of the types of questions we might want to ask our graphs, and we might sort of see the difference about how we ask questions of graphs versus how we ask questions of structured data, or how we ask questions of linear data or something like that. So primarily we can think about construction given some set of paths or vertices. Is there some sort of construction possible, right? Can we come up with a graph that is bipartite, meaning that there are a set of nodes on one side that can fully connects with a set of nodes on another side? Do we have a fully connected network, right? Meaning that everything is attached, that can traverse everything else? Or do we have all these sort of little subgraphs going around? We can think about enumeration, right? We're statisticians. What can we count, right? Can we count how far things are? Can we count how many neighbors we have, right? Can we filter and start to ask, what is the shortest way to get places? We can talk about existence, right? When you start to query graphs, you can say, is there some set of vertices or edges possible that meet this particular criteria, right? That sounds a lot like a predicate on a structured query, right, in SQL or something like that. And the really great thing about graphs is we can also start to think about optimization, right? What is the shortest path? What is the minimum spanning tree, right? How do we create a subgraph that exhibits these more optimal properties over our large graph? And in broad strokes, these are the types of algorithms that computer scientists work with. Now, and the primary way that you affect these algorithms is through something called traversal, right? So you have a starting node or a starting set of nodes, and then you traverse out along the outbound edges to other nodes, and then you continue traversing until you have met the question that you've answered, collecting information along the way. And hopefully you can see that this is where that sparsity that we just talked about really has big benefits, because you don't have to know the entire domain. You don't have to know the entire data space in order to do these types of traversals. In fact, you start thinking in local contexts, right? So what's the locality of the information that I'm trying to discover? And then you move out, and you can bound how far you move out in order to get yourself discrete discrete answers. You can add randomness, right? So you can add random traversals in order to get stochastic algorithms, but this is the primary method. One of my colleagues, when she first saw this visualization, said, well, that looks a lot like a geographic map, right? That looks like a lot like a road system. And I think that's great, because that's a great way to think about how we perform this type of computation. Now, we need a model. Because we're data scientists, we need to embed data in here somewhere, and the data in graph land comes in the form of a property graph. So a property graph is composed of structural elements, and every structural element has key value pairs associated with it and a unique ID. So there is this combination of both structure and data inside of these graphs, and it can be simple or it can be very complex data, right? So that's sort of important to note. The primary structural element is the graph, right? The graph itself, or a graph, and you might be working with multiple graphs, as we'll see later. The graph is the object that contains vertices and edges. And that's very important, but it's also important to note that the graph can also contain key value pairs, right? So one that I always put on my graphs is like a title. Like the name of the graph is this, so I know what I'm looking at. The graph can represent the entire data set, right? Or it can represent like a select, a query, a subset of your data. And we're going to see later on how we use views to pull out subgraphs for filtering and selection. The next two elements are probably a little bit more familiar. The vertex is an object with incoming edges. So if this entire image of the sort of graphs of the Olympic is the graph, then these circles are the vertices. And you can see that the vertices have incoming and outgoing edges. So you can't really see the arrowhead there, but they have sort of these connections to other vertices, and they also have key value pairs, right? So here's the VID4, right? Every graph element has an ID, and then the type is an athlete, and the name is Michael Phelps. Here's a different type. This vertex is an event, right? And it has a name property and a unique index. And you can see that we can actually embed, this is a multi-domain model, right? This isn't a single table. We have events, we have athletes, we have countries, we even have the entire Olympics here as sort of like the root node for the 2016 Olympics. Finally, edges are objects with a source, right? So here's the source vertex, and then the target vertex, right? So the vertex embeds that. In property graphs, vertices have this special type ID that sort of says what thing this is, and you can sort of think of these things composed into tables of different types. Similarly, edges have a label, right? So this edge is competed in, right? So Michael Phelps has competed in the 4x100 meter men's medley relay. And then we can add other sort of properties onto this as well. You can also think about weights and different types of properties that you might want to put on this graph.
Can I get a quick question?
Sure.
So isn't that the abstraction for an SQL query?
Okay, so the question is, isn't this the abstraction for an SQL query? And I think it's probably not, right? I mean, unless you think of this as like a really massive join with different foreign keys, but think about the fact that this actually might be a many-to-many relationship, which might be an embedded table there. So this much simpler, much more compact representation actually expands when you think of it in the set context, right? So in a relational database, these are all sets of things, and you have to think about the intersection of these sets. So it's a little bit different. So the question for today is about dynamics, right? So how do we model time in these graphs? And it turns out that in order to start that, let's think about a relational database. Since you brought it up, right? I magically got this slide in here. So how do you model time in a relational context? Well, if you think about an ER diagram, you might be thinking, hey, we're pretty close to a graph, right? And so we can have these entity tables, and entities have columns on them. And so what we can do is we can add these descriptive time elements, right? Created and modified. And here's the issue with that. If you update created, or probably you would update modified, right? That changes that entire row, right? You get no history associated with that. So if you want a history, you have to create something like an event table, right? So where the event has, each row is a discrete time, right? So you can see I have occurred, I might have a duration on here, you might have an interval if two date times are given, right? These things are represented as date times with time zone or something like that if you're using PostGIS. Postgres. And so the event table is an append only, right? All you do is insert rows to the bottom of this thing, so it's always growing. If you want to have relationships, so for example, if you have this foreign key between an event and an entity, you cannot embed time in that foreign key unless you use an intermediate table, a relationship table. So this sort of structure, when you're doing time series analysis in a database, is very common. So common, in fact, that there are databases that are optimized for time series analysis, like InfluxDB. And what InfluxDB does is it supports really fast appends to these types of tables, and it makes these guys a first-class element in the database, right? But they sort of still suffer from having to maintain all of this information. How about in a graph? Well, in a graph, we can put time as a property, right? So on this vertex, it's a last seen time, right? We can put a participated time on the edge, started, finished, right? We can put build time on the edge here. This thing generates this. We can encode ordinal time without any timestamps at all. This event precedes this event, precedes this event, precedes this event, and so on and so forth. We can put timers in here, like elapsed, right? Where's elapsed? Or look at sort of last seen and take deltas there. Here's build time, that's probably elapsed. We can even put in predicted times, like here's a vertex that's grayed out. This is an event that we are waiting for. This hasn't occurred yet, right? This is something we really couldn't embed in a relational model unless we just had left the timestamp as null and we had some way to reason about that. So hopefully what you see here is that in the property graph model, time gets added in as properties, but also in sort of the structural elements too. So there's a lot of different ways to encode time, and this is much more compact. And I hope you'll also see that this is a little bit more easy to understand, right? It's sort of easy to understand the sequence of events right here. Yes, please.
Clarify, you're talking about actually creating additional nodes that are pointing one-to-one to a specific additional node that you could have attached that property to, right?
Possibly, and in fact I will talk about doing exactly that. But here, these things are the events from that event table, right? And we just have a relationship between events in the relational database.
That you don't have history of how these timestamps are changing, right? Unless you're adding multiple nodes pointing to that specific node saying
Okay, yeah, so that's a good point. So you have to have multiple nodes here going throughout history, but you have it in this more compact representation, I would say. Okay, so now that we've got time in our graph, remember I told you there's all these graph algorithms, so what do we do with it? Well, time modifies traversal. So the first thing we think of is that traversal can be bounded by time, so you exclude paths, you don't go down a path unless that's too recent or that's been expired. Finally, you can use centrality measures, which I'll talk about in a little bit, that can weight time, and by doing this, you can start to model decay, right? So how long ago was it, and what is the weight of that relationship of time? And the next thing you can do is you can use tentative or future edges, which you saw in the last graph. So let's take a look at a specific example. So this is an example that I have extracted from my email mbox, which you can download from Google or export from Apple Mail using a tool called Tribe, which is another District Data Labs open source tool. And what I've done here is I've constructed a multi-graph. So every one of the vertices are email addresses, and an edge is an email sent between two email addresses. So you might think about from to or CC. There's a lot of different things you could do here, but it's a multi-graph because as long as there are more than one email sent between these two email addresses, that you add an edge for every one, and you can include the subject and the sent timestamp. That's where the time property is here. So if you look at my email node graph, you can see just counting things. I have 6,174 nodes, that's unique emails in my email mbox, with 343,000 edges and an average degree, right, which means the number of outgoing edges, of about 111. And if you take a look at that, this is one graph visualization that's hierarchical. You can see the nodes are sort of on the outside around, and then these colored lines indicate their edges to other nodes. And you can see it's kind of a mess. One thing I forgot to mention, and I apologize, is that all of the Python in this is going to be using Graph Tool, not NetworkX. So sort of a surprise there. Graph Tool is a new library that has C implementations, and it's a lot faster than NetworkX, so long as you can get it compiled on your computer, which is kind of a big if. But they are working on it and developing it, and you can do a lot. You know, you can get sort of medium to large size graph analytics happening with Graph Tool, things that would not really be possible using NetworkX. And in particular, I like it for the visualizations. What I've been saying is that Graph Tool is replacing Gephi for the types of graph visualizations that I do for me personally.
Is that the one that's demoed on your GitHub?
Yes, Graph Tool is demoed, but there's also some NetworkX in there too. So here's what we're going to do. We're going to do a time filter traversal, and you're going to see your first example of subgraphing here. So the way that Graph Tool works is it creates a view, which is essentially a new graph that has pointers to the vertices that match some filter property. And you can have either vertex or edge filters. So what I like to do is I like to create these factory functions, so def cent range, and you pass in the graph and a before timestamp or an after timestamp, and it returns a closure that the closure takes as input as an edge, and then computes whether that edge belongs in this graph based on its cent timestamp. And so this function will be applied to every edge in the graph. Similarly, this is a tool that we're going to be using a lot. This is a degree filter. So we're going to return a vertex filter function where we say that the vertex has to have a degree greater than this degree, right? So if we remove a bunch of edges and then all of a sudden we have emails with, that don't have any sent emails between them, this will help us get rid of them so that we can, see things a little bit more clearly. And then this is what happens, right? So you can see here I have my graph of emails, and you can see there's 6,000 vertices and 343,000 edges. I apply this cent range filter, so everything after August 1st, 2016. And then here's the graph view that it does v-filt with the degree filter and e-filt with this August filter. And what comes out is 843 vertices and 24,813 edges, something that's a little bit more understandable when you take a look at it, right? And in fact, I could even do things like eliminate hapaxes, right? Like things where there's only one email address here, and probably make this a little bit more understandable. And I can start to look, okay, what's happening in my email for this month, right? From August 1st to August 30th or something like that. So we now have a mechanism with which to compute on time. But the next question is, what makes a graph dynamic, right? We're interested in change over time. So there's two primary methods. The first is what you alluded to, is actually adding time as a structure, adding it as a vertex or a node itself. And the second is to make dynamic graphs, and dynamic graphs are structures that have multiple graphs. But before we can get to this, we first have to understand the granularity of time, because in both of these measures, we can only encode time as discrete events, right? Discrete time steps. Now that doesn't mean that we can't encode ordinal time, right? We just simply order the time and say timestamp 0, timestamp 1, timestamp 2. And if we want to encode continuous time, we have to say that the time is the continuous interval between two time steps, which has its own issues, but we can say that. And we also have to pick a specific granularity in order to aggregate these events and these nodes into a single structure so that we can compute upon it. And sort of understanding how this drill up, drill down works is very important, because as you drill up, right, or roll up, you're going to get fewer and fewer vertices. And as you come down, you're going to get more and more vertices. And that's going to have a large impact in the types of subgraphs that you achieve. So let's look at time extracted as an independent element. So here, what we have is we have these sort of CBEFs, and these all used to have a time property on them. And instead, I've extracted them out as this sort of discrete time thing at some, let's see, what color is that? So hours or minutes, right, this clock element. And immediately a number of things become apparent, right? You can sort of see a sequential order in how these events, you can see precedence relationships between pairs of nodes, so you can start to traverse, what follows H, right, in a meaningful fashion. And then in particular, and we'll look at this specifically, you can start to compute which vertex, which time vertex is the most important or is the most central to this graph.
How did you do this?
So this is just a graph that I drew, but we'll see a specific example when I extract week in a second. In terms of dynamic graphs, you actually need to embed multiple subgraphs, and so you'll have subgraphs over time. And what we're looking for here is what's different, right? So between T1 and T2, we've now added a node and some of our edges have changed. Between T2 and T3, you can see we've lost some nodes and our edges have changed. And so we're going to look at sort of what's the difference between additions and deletions. All right, I mentioned that we did this sort of NLP approach, so I want to talk about key phrases over time to get you a little bit more specific examples. So DDL has 2 projects that deal specifically with natural language processing. The first is Baleen, which is a corpus ingestion tool. You give it an OPML file of RSS feeds, and every hour it will sync those feeds and then go out and fetch the article and store it in a Mongo database. We've had this thing running since March, and we have about 700,000 some documents. So it's a corpus of probably about 70 gigabytes of text data. So it's non-trivial. And then we have another thing called Minky, and the hope is that Minky is going to be able to operationalize text machine learning models. So topic modeling, document classification, these types of things. And it's going to do it in parallel using a bunch of other tools so that you can quickly pre-process your corpora and sort of get to the good stuff, which is the work of actual analytics. And in particular, what Minky has done for us is it's extracted noun key phrases using a grammar that are weighted by TF-IDF, right? And so if you look at the model for our graph here, what we have is we have category, right? So there are 13 categories of, cooking, data science, news, politics, that sort of thing, sports. We have feeds, right? And feeds can belong to a category. And then we have our sort of central thing, which is the document, right? That's the article that we pulled down. Documents are attached to categories and to feeds. And then attached to the document are the key phrases, and you can see that the edges are weighted by TF-IDF. Now on our original corpus, we pulled this down and we had 2.6 million nodes, 46.9 million edges. And that crashed my MacBook Pro when I tried to deal with that. So this seems like maybe a GraphX or Spark job. It's a little bit too big for multiprocessing. So we sampled it down to about 139,000 nodes and 257,000 using a stratified sample on this category so that we have sort of an even representation based on what we got from the original data set. So let's do a little bit more data wrangling here. Remember this degree filter function? We're going to apply that again, and we're going to say that the key phrases in particular, or documents, have to have a minimum degree of 3. And the idea here is that now we're filtering out the hapaxes, the sort of unique stuff. We only really want to look at commonalities between documents. And this gets us down to about 8,500 nodes and 112,000 edges with an average degree of 26. If you guys aren't used to graph analytics, the first thing that you should do is you should take the log plot of the magnitude of all of your vertex types, and you should also look at the degree distribution. So when you see this, you can see that primarily we have phrases in our graph, and that we sort of follow this power laws curve or this power laws distribution, and that's good news because that indicates that we have a small worlds graph, which are the types of graphs that humans are particularly interested in. So we're doing good so far. Whoops. So how are we going to sort of get at and sort of see this? So the first thing we want to talk about is this ego filter, and I'm really running short on time. So I'm just going to show you one of these documents here. So the document is entitled Villanova, I can't read it from here, Alice, Iowa. So this is about an NCAA game in March, and you can see some of the key phrases include NCAA tournament, write, bracket, learn, poll. Here's the category, which is under news. And so you can see that extracting this document as an ego gets us this style shape key phrase graph, and this is drawn with Graph Tool. So let's talk a little bit about the centrality of time. So the first thing we have to do, and this gets to your question, how exactly did I do this, is I've picked week as the level of granularity for this data set, right? So we're doing it every hour, we're doing an ingestion, but we're really only collecting a couple hundred documents an hour. So let's look and see how key phrases change on a per week basis. So in order to do this, I have to go through all of the vertices, right? Check and see if they're a document, and then extract the pub date, and I can extract this ISO calendar. So here the week is like week 0 is the first week in the year, here, week 1 is the second, all the way up to week 51. And then I can just add vertex, add the week as a vertex, and then for every document link, attach that from the document back to that week. And so that's what the construction is.
Okay, how does that lead to shared nodes amongst, because the node property of like the week in which the publication happened was shared in your
Shared how?
image. Like that image that you had, like this, no, if you go back, like, sorry, whatever.
Okay.
It was like shared node, like meaning that like if 3 nodes have had the publication in the same week, they're not each going to have a vertex.
No, there's only going to be 1 week vertex.
Okay, sure.
Right, so yeah, so it's week 0. I've added at most 51 weeks to this. However many weeks there are, that's how many extra vertices I've added. Okay? So then let's talk about the centrality of time. So centrality is a measure that asks what node is the most important node, and in particular we want to know which week is the most important week. And it turns out there's a variety of mechanisms to compute the centrality of a node. So we could do it based on popularity, right? How many edges does this thing have? We can think about betweenness, right? How many shortest paths pass through this, right? How much information is contained in the information traversal? We could think about what is the average distance from this node to every other node, which is called closeness centrality. Or we could do what Google does and look at eigenvector centrality, which is a measure of relative influence, where closeness to important nodes matters as much as how popular you are. And we can also factor prioritization or do any number of sort of centrality measures. And when we look at this, you can actually see that these centrality measures have a huge impact in how they change the type of analysis that happened. So this is betweenness centrality, which is a very common centrality measure. And these weeks are ordered in terms of their importance, and then these key phrases are ordered in importance for attached to the week that they're in. So you can see that in week 49, demagogue, nobody, University of Illinois, Islamic State, those were the most important things in week 49. However, week 45 is more central, more important than week 49, and it has turnout, democratic, undocumented immigrants, etc. Cat centrality, on the other hand, is a completely different centrality metric, and you can see that everything changes. Right now, week 18 is the most important, with data, September, other words, follow Tech Insider. Week 10 is slightly less important, but its important terms are citizen, monopoly, finance, big, and efficiency. And so by sort of looking at the centrality of time, we can start to pull out or elicit different types of insights, and we can actually see how the key phrase usage changed over time, and maybe do this in the context of a category, and really get to ask very specific questions of the structure of our graphs, which is really the thing that you're doing when you're doing this type of analysis. How about dynamics? Can we actually see what happens over time? So in order to create a dynamic graph, what we'll have to do is we'll have to create a sequence of time-ordered subgraphs. And so this is week 2, 4, 5. What happened to week 3? Well, it turns out that Bailey had crashed during week 3, and we actually didn't get any documents for week 3, or they got filtered out by the Hapaxes, so that's gone. But you can sort of see how the structure of the key phrases is changing over time, right? In week 2, there are fewer, more important key phrases than in week 4, when there are tons of not so important key phrases, right? So maybe this means that the news this week was all very coordinated, whereas the news this week was very general. You can see sort of a middle ground with week 5. How is the news changing? In particular, one of the best ways to sort of look at this is using that visual analytics model that I mentioned, and animate what you're seeing. So without getting into too much detail, I would say that if you're going to start looking at animation, and this is another Graph Tool thing, right? So Graph Tool does do animation. You want to, as much as possible, fix the positions, right, of the vertices and the edge. Transitions to and from different time periods should be eased so that you can see what's changing when. The only change should be related to time in these types of dynamic graphs. So as these things are changing color, every sort of time element, every dynamic graph is being highlighted by the orange color. And finally, if possible, you should allow interactive control, because that control really gives good insights as you look at how things are changing over time. Now, I'm quickly running out of time, but I want to get a little bit into that network visualization aspect of this, particularly as we just saw how that might be the best way to do insight on the dynamics. And you might start to ask yourself, are there any automatic or structural analyses that you can do on the dynamic graphs? And the answer is yes. You can apply these centrality measures and then graph them over time and look for changes that way, and then do maybe a more routine lag analysis or time series analysis. But there is actually not a lot of work in that dynamic space on sort of coordinated or structural analysis. So if we think about network visualization, the first thing that we have to think about is layout, right? How are we going to position our nodes and edges in the graph? And there are a lot, but most of them are based on spring block diagrams, right? Using force vectors to put nodes into certain positions and then connect their edges. In terms of dimensionality, I usually say that with normal visualization, you get about 7 dimensions. Graphs, you get about the same. So you can modify based on the betweenness property or the degree or other things, modify the shape, the color, the size, even do maybe something more complex like pi nodes. My talk is coming up. You can, and then so for node type for color is what you saw, node size for their centrality was what you saw in the graphs that I did. Similarly for edges, you can change their direction, use tapering, size, and color. All of these things come from Lane Harrison that talks about how to eliminate the hairball. And I really like her talk if you want more information on visualization. But the reason I brought it up specifically is because all of these things are adjustable using Graph Tool. So these are all the sort of things that you were seeing in the visualizations I presented. But that sort of becomes like, is the question, is that enough, right? You can see that this is everything. So this is that entire subgraph. Here is the extracted weak subgraph. I don't know if there's a whole lot of insight you can get from that. So I'd like to leave you with this idea of visual analysis and the visual analytics mantra, which is overview first, zoom and filter, details on demand. And hopefully what you saw is that through dynamic analysis, overview first is subgraphing, right? Get a query that specifically looks at what you're looking for. Zoom and filter is the application of centrality properties, right? And then sizing things and maybe eliminating hapaxes and other things. And then details on demand is hopefully the visualization or the instance view or actually eliciting the properties from the graph so that you can make more coordinated insights. In my case, I simply wrote the text onto the vertices, right? And you could zoom in and see what the text was. So back to our original question. Are graphs effective for analytics? And I hope that you guys think that the answer is yes, because this was not a CS approach. This was not about algorithms or computing, right? This was about finding insight. And what graphs give you that other types of analyses don't is structure. And when you have structure, you can ask many different types of questions and really get that sort of impact of simplicity of modeling and speed to insight through visualization. And I hope that you guys will take graphs and explore them, answer some of these unanswered questions like, well, are there any statistical computations that we can make on dynamics, right? And what can we do with these as we bring these into the data science space and sort of elevate these Python tools that we all have into prominence in our workflows. And the end. Oop, that's the wrong button. The end. Yes?
So you said Graph Tool is a Python library?
So the question was, is Graph Tool a Python library? And it is. It's actually a C++ sort of bindings that has a Python API.
The question is, does it have a PySpark hook?
Does it have a PySpark hook? Not that I know of, although I am a big fan of GraphX and sort of the graph stuff inside of Spark, but I'm not sure. Yeah.
iGraph versus Graph Tool, can you talk about the differences?
What was the first one?
iGraph.
iGraph? I haven't played with iGraph, but I'd be happy to talk about the differences between, like, say, NetworkX and Graph Tool. Yeah, so speed is clearly one of them, but the other is focus. So NetworkX and potentially iGraph, they give you everything, right? Anything you could possibly want to do to a graph, like NetworkX has the function to do that or the method to do that. Graph Tool is way more specific in its implementations and for optimality, but also to expose a simple API to the most common types of analytics that you might want to to do. And like I said, I mean, Graph Tool just feels like the Gephi that Python has. Yeah.
So I saw that after the extraction is done to a JSON format, you're using Minky for further pre-processing or processing, and it involved using TD IDF. So could you not have used something readily available like Elasticsearch that takes JSON and also has
Right, so the question was, could you have used Elasticsearch for the NLP processing? And the answer is that Minky is actually using NLTK to do actual linguistic pre-processing. So it's doing segmentation, right, sentence identification, it's doing tokenization. These are all using regular expression models that have been trained on English corpora. It's doing part of speech tagging, and then it's applying a grammar. So it's actually doing a lot of sort of linguistic style work that doesn't come natively with Elasticsearch. For example, Elasticsearch by default stems, right? It chops off the affixes in the hope to get to word classes, whereas we're using lemmatization with WordNet. So Minky is just sort of doing other stuff. But yes, potentially, if you wanted a speed boost, you could use Elasticsearch.
Thanks.
Okay, well, great. Thank you all for coming. Oh, one more question.
So in your example of the analysis on the blocks, the words,
Right.
what could you put your finger on one particular insight that you think is more easily arrived at by this approach than a more traditional approach wouldn't find?
Okay, so as a tangible example. So one thing that we were looking at specifically that I didn't get a chance to look here was what was the relationship of the campaign to the news cycle, right? Because the campaign is involved in this. And hopefully you sort of caught a hint of that when I sort of listed the key phrases over time. And you could see that there were actually particular events that trumped Whoops. There are specific campaign events that sort of beat out or washed out the campaign cycle. But those things had to be like really important types of things, like the NCAA tournament, or like I think LeBron James was one of them going on. But then you could also sort of watch specifically how the campaign news was changing over time as the sort of, the different party primaries and debates were happening, and how it was moving and sort of the cycles that were happening there. And I would say that that is easier to look at in a graph structure than a different type of structure, because you're looking at the key phrase change over time. You're not looking at some aggregate change over time, right? You're not looking at like number of key phrases that's classified one way or another over time. Here you have the opportunity to omit that from your analysis, but have it be a latent factor. And in fact, in general, that's what I would say that graphs do. Graphs are structural, and the structure composes a lot of latent factors, and potentially that's what we're doing when we're looking at graphs, is we're actually understanding those latent factors in a more meaningful way.
Thank you.
All right, thank you again.